So now let's take a look at another type of algebraic process. This one is what's referred to as completing the square. So sometimes in mathematics, you're given either monic quadratics or non-monic quadratics, and they're factorizable. Sometimes you are given something in the form x squared plus 2ax plus a squared, and this could be plus or minus the minus term. This is a perfect square, which we can write as x plus or minus a all squared. The process of completing the square essentially involves taking some part of this expression, adding or subtracting a number to it to turn it into one of these perfect squares, and then contracting it. So let's look at the relationship between some of the values in this quadratic. We have 1x squared. Let's take the plus case. We'll take the plus and minus cases separately. Plus 2a times x. So this is the coefficient of the x squared. This is the coefficient of the x. Plus a squared times 1. So this is the coefficient at the end. My bracket's in the right spot. A squared times 1. So you've got an x squared term, an x term, a 1 term. These are the three coefficients. This third coefficient, the a squared is actually equal to the second coefficient, 2a, divided by 2, and then squared. So this is going to be our general process for completing the square. You're going to be looking at the b term in front of the x. You're going to be saying, okay, if I have some polynomial of the form x squared plus bx plus dot dot dot, you need to add a number to it. You're going to say, okay, take this b value, divide it by 2, and then square it. That's going to be the term that we add to the end in order to make this a perfect square. Once you've done this, it will always factorize, and it will factorize into the form of 1/2 of the b term. So this will end up being x plus b divided by 2 all squared. So this is a very strange process. It's very weird to look at the sort of theory that I've got here, where I'm outlaying a bunch of um, different details about how the completing the square process works. We're going to have a look at some examples. The only thing that we really care about from all of this working is that the number added at the end is equal to the b coefficient divided by 2 squared. Right? This is always going to be the case for these questions. Whether the b coefficient is positive or negative, the c coefficient will always be positive for the majority of the questions that we see. So let's do some examples, because the theory of this is a little bit confusing. So let's imagine you're given the following. You are given x squared plus 8x plus dot dot dot, and you are told to complete the square. So complete square. We need a number at the end. So we know the term in front of the x squared is 1. That's good. We know the term in front of the x is 8. Well, we just built up here a formula to tell us what term we have to add. We know the term at the end c is going to be the term b divided by 2 and then squared. So this is going to be 8 divided by 2 squared. 8 divided by 2 is 4. 4 squared is 16. So we have to add 16 to the end of this expression. So this whole expression now becomes x squared plus 8x plus 16. If we now try factoring it, we will find that two numbers that add to make 8 multiply to make 16 are 4 and 4. So this becomes x plus 4 times x plus 4, which is x plus 4 all squared, and this is our perfect square that we were after. So this process of completing the square allows you to take an expression that's essentially, it's got a quadratic term, it's got a linear term, it's missing a number term most of the time, and it allows you to find what number term would turn those two, the quadratic and the linear term, into a perfect square. Once it's in a perfect square, then you could potentially use it for things, right? So in the next video, we'll look at solving equations with perfect squares. There are many equations that are easier to solve if you're using perfect squares. There are many formulas that are easier to prove using perfect squares. So I'm going to let you have a go at two complete the square questions. So I'm going to say question 1 is a squared minus 10a plus dot dot dot. You have to find what term you add to it and then find what the perfect square ends up being. And for question 2, we'll make this one a little bit harder. I will say that you are given 2a squared and then plus 12a plus dot dot dot, and you have to find how this would turn into a perfect square. So what term you would add to the end of it to make it into a perfect square. If you have a non-monic for these questions, usually you're going to start by factoring that. So that's just a little detail about question 2. So I'd like you to pause the video now, have a go. Okay, so now that you've done this, let's complete the square on these two examples. Now, these two examples, they're not very hard, but complete the square is slightly complicated. Students often don't really understand what's going on. So even though these aren't very hard examples, you could get these in exams because the teachers are aware that students tend to struggle with completing the square. So we have a squared minus 10a. Well, the b value, the term in front of the linear term, is minus 10. So the term we're going to have to add to the end, c, is equal to minus 10 divided by 2 squared. So this is minus 5 squared. This is 25. So this becomes a squared minus 10a plus 25. If we now factorize this, it will become two numbers which add to make minus 10, multiply to make 25. That's minus 5 and minus 5. So this becomes a minus 5 squared, and that's our perfect square. So that's question 1 done. So question 2, this is a little bit harder. We need to work out what number we need to add to this to complete the square. If it's a non-monic, completing the square is harder. So we're going to factorize this. We're going to say, actually, this is 2 in front of a squared plus 8a plus the dot 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 is just a missing number, so we'll still just write that as dot dot dot. Now we're going to do complete the square for the bracket. So c is going to be equal to the number in front of the a term, 8 divided by 2 squared. So 8 divided by 2 is 4, this is 4 squared, this is 16. So we have to add 16 inside the bracket. So this whole thing becomes 2 times a squared plus 8a plus 16. Now, if we factorize this, two numbers that add to make 8, multiply to make 16 are 4 and 4. This is a plus 4 times a plus 4. And this we could write as 2 times a plus 4 squared. So the number we added once we had factorized was 16. And that means in the initial expression, if you asked for this detail, you would have had to have added 32. Because once you factored the 2 out, the 32 would have gone down to a 16. So this is the answer to question 2.